Picture the scene of a girl's 10th birthday party. Pink balloons, silver streamers, and a unicorn cake. That was my birthday party, and it was the most terrifying day of my life. As my grandmother was serving the cake, she collapsed. The paramedics came and they said it was her heart. How could someone seem fine one moment, but collapse the next?
It was then that I wondered, what could be done to detect heart problems before emergencies happen?
This question motivated me to code software that predicts heart disease risk by analyzing patient information. I'm Sophia Tomov, and my project is HeartSmart, a novel deep learning innovation to improve heart disease diagnosis.
Heart disease is the #1 killer worldwide, and 1 in 3 people are misdiagnosed. Every 40 seconds, one person dies of heart disease. The problem is that doctors' basic screening tools can be inaccurate and slow.
I created a software tool called Hero. Hero, or Heart Evaluation for Algorithmic Risk Reduction and Optimization, uses novel deep learning methods.
Here's a bit about how deep learning works. Deep learning teaches a computer to learn from existing data and predict outcomes for new data using multiple processing stages. My research uses a novel combination of deep learning optimizations known as regularization and hyperparameter tuning to predict the probability someone has heart disease based on 11 metrics of patient data. A deep neural network mimics the brain by using an iterative procedure. It's connected by nodes, or artificial neurons, and layers, or connection-making steps. Part of the challenge of coding a deep neural network is structuring it so it balances accuracy on training data and accuracy on test data. If a network is too accurate on familiar training data, it can be unable to apply itself to new data, an issue known as overfitting. But if it's not accurate enough on training data, then the network won't have enough information to accurately predict outcomes for new data.
When I first tested my variable layer neural network, I was only getting mediocre accuracy. Then I realized I had to get more creative. So I did some more research, took some online classes, and I came across these optimizations: regularization and hyperparameter tuning.
Hyperparameter tuning is a procedure that finds the most accurate combination of hyperparameters, or values that set the mathematical model. Some examples of hyperparameters include number of layers, number of nodes per layer, and the rate at which the algorithm minimizes the error margin. Regularization is an optimization that prevents overfitting and reduces the impact of data outliers.
I had learned about these optimizations individually, but then I had an idea. What if I combined the two? This is the novel Hero framework.
Here's how I tested my software. First, I coded 2-layer, 5-layer, and 7-layer models to compare the accuracy of each one. Then, I applied the optimizations to the most accurate basic framework. I used the University of California Irvine Machine Learning Repository dataset with 11 features of patient information, including age, cholesterol, blood pressure, blood sugar, and chest pain type. Based on existing research, I decided to divide the dataset into a set ratio of 2/3 training data and 1/3 test data.
When I ran the optimized Hero algorithm, it achieved 99% accuracy.
The graph on the left shows Hero's percent accuracy over 6,000 training iterations, and the graph on the right shows how regularization is effective at increasing accuracy on test data. These graphs show the accuracy of the other models I tested, and how they iteratively minimized the error margin.
When I saw that Hero achieved 99% accuracy, I was thrilled, and I wondered, could this be too good to be true? This motivated me to run statistical tests such as Matthews correlation coefficient, k-fold cross-validation, precision, and recall.
Cross-validation shuffles the dataset like a deck of cards and is used to measure accuracy on a variety of unfamiliar data. Matthews correlation coefficient, or MCC, considers performance on all possible classification outcomes, used to measure accuracy independent of dataset bias. Precision and recall measure relevant outcomes, in this case true positives.
Hero achieves extremely high performance on these tests: 0.98 MCC, 1.0 precision, and 0.99 recall. This shows how my research fits into the larger context of the field. It outperforms previously published results. This can help doctors make more accurate diagnoses.
This research won first place in medicine at the Intel International Science and Engineering Fair, the world's largest science competition. After receiving this recognition, I was further motivated to make my work accessible to doctors. Here's how a doctor will actually use the product, with screenshots from the user interface to demonstrate. First, a doctor enters 11 metrics of patient information. Then, a doctor runs the algorithm with the click of a button. Within seconds, the doctor sees the probability that this patient has heart disease. I gave my software to several doctors, and according to Dr. Maisha Taylor of University of Texas Southwestern Medical Center, having the HERO tool that helps risk stratify will guide treatment and decrease morbidity and mortality. Dr. Jeffrey Hirsch of the University of Tennessee Medical Center states that the HERO software will help doctors recommend treatment and prevent unnecessary invasive procedures.
After talking to these doctors, I realized there was still more I could improve in my project.
Originally, my algorithm considered thallium scan and fluoroscopy test results in its evaluation procedure. These tests are invasive, risky, and expensive. Because my goal is to create an accessible software tool that minimizes risk, I went back to my dataset, eliminated these two tests, and retrained the algorithm.
I was amazed to discover that HERO achieves approximately the same accuracy without these two features, meaning that the algorithm can use only data from a comprehensive physical. This makes my software easier for doctors and safer for patients.
The next challenge I faced was how to get this potentially life-saving technology out into the world. I developed my project into a business as well as a nonprofit to help get the HERO software in widespread use. My business was awarded first place in the Boyd Venture Challenge, the University of Tennessee's largest business competition. I'm donating my software to clinics in under-resourced areas in Tennessee, Bulgaria, and Brazil, and hope to expand in the future. My family is from Bulgaria, and Bulgaria is facing a shortage of doctors, especially cardiologists. Heart disease-related deaths are on the rise in Bulgaria and in Brazil due to the lack of diagnostic resources. My software will provide doctors with a free tool to make more accurate diagnostic screenings. The University of Tennessee Medical Center cardiology practice with over 2,000 patients is committed to using my software. I am working with Dr. Jeffrey Hirsch to test my software with real patient data and implement it in the practice. Heart disease kills one person every 40 seconds. In the time of this 7-minute video, heart disease killed 10 people.
No one should have to live in fear of lurking heart disease. My project can save lives by helping doctors make more informed diagnoses and recommend effective treatment to improve patient outcomes.